In the previous lecture, we were looking at correlations for heat and mass transfer at high Peclet number, and I told you that there are two different kinds of regimes, a low Reynolds number regime and a high Reynolds number regime. Note that Peclet number is ratio of convection and diffusion for mass or energy. Reynolds number is ratio of convection and diffusion for momentum. Okay. In gases, the diffusivities of mass, momentum and energy are all comparable. Okay. So, numerically they are approximately the same. Therefore, if the Peclet number is large, the Reynolds number will also be large. For momentum, for liquids, the mass diffusion coefficient is much smaller than the momentum diffusion coefficient. Okay. So, since the momentum diffusion coefficient is much larger than the mass diffusion coefficient, you could have a regime where the Peclet number is large, there is ratio of convection to mass diffusion is large, but the ratio of convection to momentum diffusion is small, or the Reynolds number is small. Okay. In that particular case, when the Reynolds number is small, as I said, that corresponds to less than Reynolds number less than 1.5 for flow past a spherical particle, and for the flow in a pipe that corresponds to a Reynolds number less than about 2100. Okay. So, when the Reynolds number is small, the velocity profile is what is called linear and self similar. That is, as you increase the flow rate, the profile does not change, only the maximum velocity or the average velocity changes. Okay. So, the velocity at a particular distance from the axis of the pipe, when divided by the maximum velocity at the center, is exactly the same, even though the average velocity is increasing. Okay. Similarly, for the flow around a particle, the velocity at any point in the fluid divided by the free stream velocity remains unchanged as the free stream velocity increases, provided the Reynolds number is small. And therefore, the Peclet number can depend only upon that particular characteristic velocity and not on the Reynolds number itself, and therefore, the Nusselt and Schmidt number depend only on the Peclet number. For high Peclet number, low Reynolds number. When the Peclet number and Reynolds number are both large, then the velocity pattern or the velocity profile does change as the average velocity changes or the free stream velocity changes. And in that case, it has to be a function of both the Reynolds number and the Peclet number. Okay. And we had looked at correlations for a pipe flow, for laminar flow in a pipe. For high Peclet number, you get a correlation that is proportional to Peclet number to the 1/3 power, okay, for the flow in a pipe, and we had expanded that out. It does depend upon the ratio of the diameter to the length, okay, and there is usually a correction for the viscosity as well. Okay. In a turbulent flow, it is proportional to the Prandtl number power 1/3, but Re power 0.8, okay, and that correction to the viscosity due to the temperature variation is still there. Okay. So, let us solve a concrete problem on how these correlations can be applied in order to estimate the transport rates. Okay. So, heat transfer in a pipe. Okay. We will consider heat transfer from a fluid of density 10 power 3 kg per meter cubed. This is the density of water typically, okay, and viscosity, which is 0.1 kg per meter per second, okay, flowing with a average velocity, okay, which is or rather specifying the flow rate, okay. Flow rate, I will call it as V dot, the volumetric flow rate is 100 liters per hour, okay, through a pipe of diameter 2 centimeters and length 4 meters. Okay. And the temperature difference between the wall of the pipe and the bulk of the fluid is maintained at delta T is equal to 50 degrees centigrade. Okay. And what we would like to find out is what is the total thermal energy transported per unit time across this pipe. Okay. And for this I also need to know the thermal properties of the fluid that is flowing in the pipe. So, the thermal conductivity is 0.15 okay, watts per meter per degree centigrade. The thermal conductivity can be expressed as an energy transport rates per unit length per unit temperature interval. That temperature interval can be expressed equivalently as Kelvin or degrees centigrade, okay, because an interval of 1 Kelvin, temperature difference of 1 Kelvin is equal to a temperature difference of 1 degree centigrade. Okay. So, these are two equivalent measures. Okay. And the specific heat is equal to 2 into 10 power 3 joules per kilogram per degree centigrade. Okay. So, these are the thermal properties, and for this length of 4 meters we need to know how much heat has been transferred across the pipe. Okay. So, for that we have to use a correlation, and first we have to decide which correlation to use, whether it is a laminar or a turbulent flow correlation, and that depends upon the Reynolds number. If it is less than about 2100 we will use a laminar flow correlation, and if it is greater than about 2100 we will use a turbulent flow correlation. Okay. To calculate the Reynolds number we need to know what is the velocity, and the average velocity has to be calculated from the volumetric flow rate. Okay. The volumetric flow rate that we have is equal to 100 liters per hour. Okay. Note that 1 liter is equal to 10 power minus 3 meter cubed. Okay. We have to convert everything to SI units first. Okay. So, this is 10 power minus 3. So, 100 into 10 power minus 3 meter cubed divided by 1 hour, which is 3600 seconds. Okay. That is the volumetric flow rate, and you can do that calculation to get this as 2.78 into 10 power minus 5 okay, meter cube per second. Okay. That is the volumetric flow rate. Volumetric flow rate divided by cross sectional area is the velocity. So, the average velocity is equal to V dot by the cross sectional area, that is pi d square by 4, okay, which is 2.78 into 10 power minus 5 okay, meter cube per second divided by pi into 0.02 meters. 2 centimeters is the diameter, that is 0.02 meters is the diameter of the pipe, this square by 4. Okay. And you can do this calculation again and get the velocity as 8.8 into 10 power minus 2 meters per second. Okay. Now that we have these quantities, we can now estimate the dimensionless numbers. The Reynolds number, okay, which is equal to rho, okay, which is 10 power 3 kg per meter cubed into 8.8 10 power minus 2. and you can see that the dimensions on numerator and denominator will cancel out, and if you do the calculation, this turns out to be about 17.68. Okay, this is the Reynolds number, much less than 2100 laminar flow regime. Okay. And the Prandtl number, which is Cp times mu by K. Okay. This Cp is 2 into 10 power 3 joules per kg per degree centigrade into mu is 0.1 okay, divided by K, that is in this case 0.15 watts per meter. Okay. And this turns out to be 1.33 into 10 power 3. Okay. So, you can easily verify that the Peclet number, the product of the Reynolds and the Prandtl numbers, is actually large in this case, but the flow is still laminar because the Reynolds number is less than 2100. Okay. So, therefore, I have to use the laminar flow correlation. Okay. The Nusselt number is equal to 1.86 into the Reynolds number power 1/3, the Prandtl number 1.33 into 10 power 3 power 1/3 into d by L power 1/3. Okay. D is 0.02 by 2 meters by 4 meters power 1/3. Okay. And you can do this calculation and get a value of 9.12. Okay. So, that is the Nusselt number. Okay. The total heat transfer rate, okay, the total heat transfer rate, okay, is equal to the surface area of the pipe wall, okay, pi dl, okay, pi dl, okay, into the k delta T by d into Nusselt number. Okay, or let me just make another step here. Okay, so, times q average, the average flux, pi dl into the average flux, okay, which is pi dl. The average flux is k delta T by d into the Nusselt number. Okay, the average flux Nusselt number is defined as the flux divided by k delta T by d. Okay, so, this is equal to k delta T by d into the Nusselt number, and you can see that the diameter will cancel out on both sides, and I will just get pi L k delta T Nusselt number. Okay, so, that is the heat transfer rate per unit time. Okay. I can substitute for the numerical values. Length is 4 meters, the k is 0.15 watts per meter per degree centigrade, delta T is 50 degrees centigrade, and the Nusselt number is 9.12. Okay. And if you do this calculation, you will get the heat transfer rate as 860 watts. Okay, so, this is an example where you can use the correlation to actually estimate what is the heat transfer rate across the wall of the pipe, okay, in order to find out the rate of heat transfer. You can solve this problem the other way, okay, and that is that for a given heat transfer rate you can ask what is the length, okay. And the length in this case you can see that the correlation, okay, has d by L to the 1/3 here. Okay. Okay, so, the total heat transfer rate will go as d by L to the 1/3 times the length. So, it will increase proportion to length to the 2/3 power in this case. Okay. Okay, so, this is an example where the correlation is used in order to estimate what is the heat transfer rate. Okay. and as I said, if you if on the other hand if you calculated the Reynolds number and it turned out to be higher than 2100, then we have to use the turbulent flow correlation, okay, 0.023 into Re power 0.8, okay, and PR power 1/3. So, that was the correlations for the flow through a pipe. Okay. Let us look at the correlation for flow past flat plates. Okay. Recall, the flat plate flow is basically a flow past an object of infinitesimal thickness. Okay. The velocity upstream of the object is the free stream velocity, okay. And as the fluid encounters the object, there is a 0 velocity condition at the surface, due to which there is retardation of the flow at the surface, okay. And as momentum diffuses from the surface, the length scale over which there is a retardation due to the surface increases. We can define the boundary layer thickness as the thickness at which the velocity reaches 99% of its free stream velocity. This was defined as this thickness was defined as delta of (0.99). Okay. Okay. And this increased proportional to x power 1/3, okay, as we went downstream. Okay. It increased proportional to x power 1/3 until the point at which Rex is equal to V free stream x by nu is equal to 5 into 10 power 5. Okay. Okay. Until the downstream location at which Rex is equal to 5 into 10 power 5. Okay. At this point there is a transition to turbulence. Okay. So, we have a laminar flow here and a turbulent flow here. Okay, where you have velocity fluctuations, and this happens when Rex is proportional to 10 power 5. In the laminar region, delta of 0.99 is proportional to Rex power 1/3, okay, into x. In the turbulent region, sorry, Rex is half. Okay. So, in the laminar region, the boundary layer thickness is proportional to Re power minus half into the downstream distance. In the turbulent region, it goes as Re power minus 1/5 into x. Okay. So, obviously, the correlations will be different in these two, the laminar and the turbulent regions. Okay. I told you when we discussed the analogies between heat and mass transfer that this is one particular case where the Reynolds analogy holds. Okay. And because of that, we get correlations from the friction factor. We can determine what are the correlations for heat and mass transfer, okay, in the flow past a flat plate. Okay. For a laminar flow, the Nusselt number is equal to 0.664 Re per half, okay, into PR per 1/3, okay, and mu by mu w per 0.14. Okay, this is the correlation for the Nusselt number in the laminar flow past a flat plate. Okay. Recall that we had a correlation for the friction factor was equal to 1.328 into Re per half. Okay. And the analogy states that the Nusselt number is equal to friction, the J factor is equal to the friction factor by 2, and this satisfies that, okay, for the flow past a flat plate. Okay. And for a turbulent flow, the Nusselt number is equal to 0.037 Re power 0.8 PR per 1/3 mu by mu W for 0.14. Okay. So, these are the correlations for the flow past a flat plate for heat and mass transfer. This is the heat transfer correlation. For the mass transfer correlation, you substitute the Sherwood number for the Nusselt number and the Schmidt number for the Peckley number, and you will not have these correction factors due to the temperature. Okay. This mu by mu W, mu is the viscosity of the fluid at the temperature far from the surface, and mu W is the temperature, is the viscosity of the fluid at the surface itself. Okay. So, this is a viscosity correction. Okay. So, this is the heat and mass transfer correlations for flow past a flat plate. Okay. Next, we look at, okay, flow around a particle. Okay. So, basically you have the flow around a particle in which there is some free stream velocity far from the particle. V free stream. Okay. Particle has diameter d. Okay. Now, if you are in the limit of high Peckley number and low Reynolds number, I told you that the correlation depends only on the Peckley number. That is because when the Reynolds number is small, for a spherical particle less than about 1.5, there is symmetry between the upstream and the downstream sides, and the velocity at any point is proportional to the free stream velocity as the free stream velocity increases. Okay. And because of that, you get a correlation that is depends only upon the Peckley number, but does not depend on the Reynolds number. Okay. And for this high Peckley number and low Reynolds number case, you can do a more exact calculation and get a correlation for the Nusselt number or the Sherwood number, okay, which is equal to 0.992 PE per 1/3. Okay. Of course, this applies only for a low Reynolds number flow, okay, for a low Reynolds number and a high Peckley number. Note that for we had earlier seen that for low Peckley number, the Nusselt number and the Sherwood number are both equal to a constant, which is 2 for a spherical particle. Okay. It can be different for a different shaped object, but for a spherical particle this is equal to 2. Okay. So, each of these correlations is limited in scope, even though these are things that we can actually derive, as we will see later in the course. Both of these correlations are limited in scope, in that they are applicable only either to low Peckley number or to high Peckley number and low Reynolds numbers. Okay. For high Peckley number and high Reynolds numbers, you have to rely on empirical correlations, and there are several empirical correlations. One of these, the Nusselt number or the Sherwood number minus 2 is equal to 0.6 Re per half times the Prandtl or the Schmidt number per 1/3. Okay. This is called the Rans-Marshall correlation. and this is generally applicable for Reynolds number less than about 200 and Prandtl number 0.7 less than Prandtl number less than about 380. Okay. Okay, this is based upon empirical correlations based upon experimentations. Okay, this is one correlation. The minus 2 on the left hand side is because 2 is the value for a low Peclet number, and the right hand side is a correction due to the Peclet number effects. Okay. And similarly, you have another correlation called the Whittaker correlation. Nusselt-Sherwood number minus 2 is equal to 0.4 Re per half plus 0.06 Re per 2/3 okay, times Prandtl number or Schmidt number per 1/3. Okay. So, this is another correlation which is accurate within 30% for okay, and 3.5 less than the Reynolds number less than 7.8 into 10 power 4. Okay. So, these are the limits of accuracy of these correlations. Okay. So, these can be used to estimate the relations between the dimensionless fluxes based upon the Reynolds number and the Prandtl number. Okay. Note, in all of these cases you have Prandtl Schmidt number to the 1/3 power appearing everywhere. Okay. Even in this case, the Peclet number is Reynolds number times Prandtl number. Okay. So, there is a 1/3 power. Okay. In all these cases you have a 1/3 power for the Prandtl or the Schmidt number. Okay. And this is the basis of the Chilton-Colburn analogy, where they divide the dimensionless flux by Prandtl number or Schmidt number to the 1/3 power. And we will see later in this course how that 1/3 power arises because of a balance between convection and diffusion close to the surface. Okay. And this 1/3 power will also be present for other types of objects. Okay. The flow past a flat plate also had a 1/3 power, flow in a pipe also had a 1/3 power. Okay. One caveat here is that, as I said earlier, these universality or the equivalence of the correlations for heat and mass transfer depends crucially on the properties not being dependent upon temperature. Okay. The temperature dependence is incorporated in that viscosity correction that we had earlier. Okay. If the properties do depend upon temperature, okay, the correlations may not work as well. Okay. And therefore, you have to use these only in cases where you can use where you can where the properties can be assumed to be approximately a constant. For the transport from a particle, so for example, if you had a drying droplet or something like that which was drying in air, then the transport takes place due to two mechanisms. One is due to one is the mass transfer, that is the moisture leaving the droplet, but also you have to provide the latent heat, okay, for the moisture in the droplet to be evaporated, okay, and that requires a temperature difference, and both of these occur simultaneously. Okay. Therefore, heat and mass transfer in this case are coupled, and we will look next time at a problem where there is a coupling between the heat and mass transfer and how to solve for both heat and mass transfer and design the process in such a way that the heat and mass transfer are completed, okay, at the same rate, so that the particle dries, okay, within a fixed time. I will continue this in the next lecture. I will see you then.